This question asks you to identify which statements accurately describe how changing the settings, hyperparameters, in a Gaussian process regression model with an RBF kernel affects its predictions. It's a test of your understanding of this specific machine learning method. We need to find the best settings for the model. I can do this using a systematic search, like grid search, trying all combinations of settings, or a random search, trying a random selection of settings. I'll measure how good the model is using the negative log likelihood, aiming to maximize it. That means improving how well the model fits the data. This refers to the process of finding the best combination of hyperparameters for your model. Think of it like tuning a musical instrument. You adjust different settings until it sounds perfect. In this case, perfect means the model makes the best predictions. This refers to how the data is prepared before being input to the model. Imagine you have data with vastly different ranges. The RBF kernel is sensitive to this. It doesn't treat all features equally. For instance, if one feature's values are in the millions and another is between 0 and 1, the larger feature will dominate the model. So, we'll often standardize the data, transforming all features to have similar ranges, to ensure they're treated equally. This statement is false. The radial basis function, RBF, kernel's performance depends strongly on the scale of the input features. If not scaled, some features may have an unduly large influence. Gaussian process regression is a type of machine learning model that makes predictions based on probability distributions. The RBF, radial basis function, kernel is a specific function determining similarity between data points. It's kind of like judging how close 2 points are, considering various aspects. The RBF kernel measures this distance in a specific way. I see length scale as a dial controlling the smoothness of your model's curves. A higher value means you're seeing the bigger picture. Your model will be smoother, less swayed by individual data points. Think of it like zooming out on a map. Individual houses become less important, and you see the overall terrain. Conversely, a lower value is like zooming in. You see every detail, and your model becomes more sensitive to individual data points, potentially resulting in a more erratic curve. This represents how much uncertainty is in your data. A higher noise level means I am more uncertain about predictions. Imagine I'm trying to hit a target, and I have a shaky hand. A high noise level suggests my shots will be spread out more widely around the target, giving me wider confidence intervals. A lower noise level means more precise predictions. I think of the length scale and noise level as two sides of the same coin. They both affect the model's performance, but in different ways. Finding the optimal balance is crucial. We typically want a model that's smooth enough to avoid overfitting, but also sensitive enough to capture the underlying trends in your data. That's where hyperparameter tuning comes in. I'm asking you to identify which statements correctly describe how the hyperparameters, specifically the length scale and noise level, affect a Gaussian process regression model using an RBF kernel. We'll check your understanding of how these settings influence the model's predictions and uncertainty. I see this. A higher noise level means you assume more randomness in your data. This directly translates to wider confidence intervals around your model's predictions. The model becomes less certain about its forecasts. That's right. You can use systematic searches like grid search or random search to find the best combination of hyperparameters. We use a metric like negative log likelihood as our guide because maximizing it effectively minimizes the difference between your model's predictions and the actual data. I agree with this. The length scale in the RBF kernel determines how much influence a single data point has on its neighbors. A larger length scale means the model considers more distant data points as similar, which makes the resulting function smoother and less responsive to individual data point fluctuations. This statement sets the context for the question, focusing on the specific machine learning model, Gaussian process regression, GPR, and its specific kernel, the radial basis function, RBF, kernel, being used. We are going to focus on GPR with an RBF kernel and its hyperparameters. I'm asking you to evaluate statements about how changing settings in a specific type of machine learning model affects its results. We're focusing on a model called Gaussian process regression, GPR, that uses something called an RBF kernel. Think of the hyperparameters as the knobs and dials you can adjust to fine-tune the model. Let's talk about the length scale. Imagine you're drawing a curve through some data points. A larger length scale means the curve will be smoother, like drawing with a wide brush. It'll ignore small wiggles in the data. A smaller length scale means the curve will be more sensitive to each individual data point, like drawing with a thin pen, closely following every detail. The noise level represents how much uncertainty there is in the data itself. A higher noise level means you're less certain about the actual values, so the model will give you wider prediction intervals, acknowledging this uncertainty. Finding the best settings for the model involves searching through different combinations. We use techniques like grid search, trying every combination in a grid, or random search, trying random combinations, and measure how well the model performs using a metric like the negative log likelihood. We want to maximize the log likelihood to find the optimal settings. This statement is false. The RBF kernel is very sensitive to the scale of your data. If one feature has much larger values than others, it will dominate the model. To avoid this, it's crucial to standardize your features, making sure all features have a similar scale, so that the model can give each feature appropriate weight. This question tests your understanding of Gaussian process regression, GPR, specifically focusing on how the radial basis function, RBF, kernel's hyperparameters affect the model. I'm asking you to identify the correct statements about these hyperparameters and their influence on the model's behavior. This is TRUE. The length scale controls the smoothness. A larger length scale means the model considers points farther apart as similar, resulting in a smoother fit. Think of it like this: a larger brush paints a smoother picture than a tiny brush. This is also TRUE. The noise level reflects uncertainty in the data. More noise means more uncertainty in predictions, leading to wider confidence intervals. It's like shooting at a target: more wind, noise, means less accuracy. Absolutely TRUE. We often use grid search or random search to find the best hyperparameter values. The negative log likelihood is a common metric to maximize, because minimizing it means finding the hyperparameters that best fit the data. I like to think of it as tuning a radio to get the clearest signal. I see the length scale as a dial controlling the smoothness of your Gaussian process regression model. Turning it up, increasing the length scale, makes the model see data points far apart as more similar, resulting in a smooth, gentle curve. Conversely, a lower length scale means the model is picky and reacts strongly to each individual data point, resulting in a wiggly, less smooth fit. Think of it like drawing a line through points. A large length scale means a smooth line that averages out the point's imperfections, while a small length scale means a line closely following every bump and curve. The noise level represents how much uncertainty you have in your data. Imagine you are measuring something, but your measurements are a little noisy. A higher noise level indicates more uncertainty, which I model by expanding the prediction intervals. Your model will be less certain. I would widen the prediction band to reflect that uncertainty. It's like when you're taking a noisy measurement, you're less certain about your result. That is reflected in wider confidence intervals around your predictions. Data scaling is crucial for the RBF kernel because it uses distances between data points. If one feature has much larger values than others, it will disproportionately affect these distances. I need to scale features to give them equal weight. Think of it like comparing apples and oranges. If one apple weighs 1 gram and the other weighs 1 kilogram, directly comparing their weights will be meaningless. You need to standardize them to a comparable scale. Without scaling, the model's performance can suffer greatly. These are strategies to find the optimal hyperparameters for your model. Grid search systematically tries all combinations of hyperparameters within a specified range. Random search randomly samples hyperparameter combinations. I use them to find that sweet spot where the model performs best. Both strategies help to find a good set of hyperparameters, but random search is often more efficient. This is a metric I use to evaluate different hyperparameter choices. A lower negative log likelihood indicates a better model fit, that the model's predictions are closer to the observed data, after accounting for the noise. During optimization, I try to minimize this value. It's like a score: the lower, the better. I'm using Gaussian process regression, a powerful machine learning technique, with the radial basis function, RBF, kernel. The RBF kernel is a popular choice because of its flexibility and ability to model complex relationships in data. I'm trying to figure out which statements correctly describe how the hyperparameters of my Gaussian process regression model with the RBF kernel affect the model's accuracy and reliability. The length scale parameter controls how quickly the model's predictions change as you move across the input space. A small length scale means the model will be very sensitive to small changes in the input, while a large length scale results in a smoother prediction surface. Think of it like zooming in and out on a map. A large length scale is like looking at a map of a whole country. Details are less important. A small length scale is like zooming into a city map where every street and building becomes very significant. The noise level parameter represents the amount of uncertainty or noise that I expect in the data. A higher noise level means I'm telling my model that the data is very noisy, and it should be careful about overfitting. This results in wider confidence intervals, reflecting my uncertainty about the predictions. Think of it like measuring the weight of an object multiple times. A high noise level suggests each measurement could be quite different from the actual weight, so my estimate needs to account for that uncertainty. To assess the performance of this model, I consider several factors, including how well the model predicts unseen data, the model's sensitivity to noisy data, and whether the model has overfit the training data. The RBF kernel's hyperparameters significantly impact these factors.